You're listening to the Facetime with Scientists podcast, where we go into the lab or into the field to learn from scientists about their lives, their work, their struggles, and their joy. Let's go. Today, I am chatting with Emma McCarthy. You are a graduate student right at LSU. I've met you previously and been in the lab chatting with you about various different projects, so I'm super excited to talk with you today about all things material science and science communication and life as a scientist. But can you tell us a little bit about where you are today? Your lab is very visually, aesthetically interesting with a weird little glove box back there
Yes.
and something in front of you that you've called a polisher. So can you tell us little bit about what you're doing today and where you are?
Right. So today I am in our powder metallurgy lab. So, like Paige said, I'm a grad student here at LSU, and we do a lot, and I'm specifically in a material science lab where we do a lot of powder metallurgy. So we process metal powders and we characterize them and are really focused on, figuring out their properties, how things affect their mechanical properties and stuff like that. So this is the lab where we process all of the materials and we prepare all of our samples and everything for characterization. And yes, like Paige said, we have our big glove box in the back. It's kind of the most fun thing to look at, but that's where we keep all of our powders just so that they don't oxidize or get contaminated for all of our experiments. And then today I'm going to be just doing a little demonstration on how we use our auto polisher, which is this machine right here. So basically, our auto polisher is to prepare samples for any kind of characterization that we do. Specifically, what we do is we mount our samples. So here I have just some steel that's mounted in a epoxy. And so we'll mount our sample, which is what it's called, and we will grind and polish the surface down because a lot of what we're interested in is the internal microstructure of the material and not specifically the surface. So if we were to just mount it and just characterize it like this without grinding and polishing, we'll just be looking at the outer layer of the material, which sometimes we are interested in, but most times we're not. So we grind and we polish it down to usually a mirror finish. And then we're able to look at the internal microstructure using either light optical microscopes or what we kind of specialize in is electron microscopy, which is in a whole different building. But yeah, that's going to be my process today, is what I'll show you.
That's amazing. So, I mean, just by you talking about this and explaining what you're doing in terms of polishing, I mean, it reminds me of like polishing rocks, as a
Exactly.
kid,
Yes.
like
Yes.
gems and rocks. Is it like just a really fancy version of
It
that?
is exactly a really fancy version of that. And the cool thing about the rock tumbler is that it's honestly kind of reminiscent of our ball mills, which is another huge part of our lab. So we're called the Extreme Processing and Interfacial Characterization Lab, EPIC, that's what my shirt says. And so extreme processing is going to refer to our high energy ball mills. So that's actually how we process a lot of the powder in our labs. We will put just say, if we want to make a certain kind of metal, like there is just like aluminum out in the world or steel and whatnot, it's all like you can all buy it at the store pretty much. Like it's all very well known. We all know the properties of it and everything. But if we want to make something more novel, something for a more specific use case, we'll use something like the ball mill. It's very small scale. So we can test out a bunch of different compositions. So we'll actually say we like want to take aluminum and we want to edit it a little bit, if you will. We want to add something in to maybe get a different kind of mechanical property. Say we can add magnesium to it. So we'll take aluminum powder and we'll take magnesium and we'll put it into this little vial and then we shake it around really hard, just like a rock tumbler. And so that is basically how we make our powders. So our powders are not going to be getting polished like the rocks per se, but it's the same mechanism where you just kind of shake it around and all of the powders fracture and mix together and weld together, and then it creates more homogeneous alloy. So that's funny that you bring up the rock polisher because it's very reminiscent of our high energy ball mills, which are actually just over here. That's one of them.
That's super cool.
But yeah.
That's amazing. I mean, yeah, I definitely grew up like, there was a phase of my childhood where I was collecting, right, like quartz and little gems as you would go to like the museums or whatever.
Right, right.
And you're like, oh, look at this, like geodes and all that. Um, I don't know if that was a phase for everyone's growing up, but I definitely got really excited about rocks. I guess that interest, I mean, at some point faded because I definitely didn't study any geology or anything like that
Yeah,
in
I was gonna
college,
say,
but like,
oh, I was gonna say it's funny that you bring up geology because, as you know, I think that's where the geology department asked for pictures of our lunar regolith that we also work with in the lab, which is funny because yeah, everybody has this like rock phase and whatnot. And the lunar regolith that we work on, that is very geology.
what are you kind of doing right now in terms of getting prepared?
So our auto polisher is a very nice upgrade that we had. Whenever I first started in this lab, we didn't have an auto polisher, so we would have to do everything by hand. So essentially what's going on is we're putting our samples against a grit paper. This is the lowest grit that we start with. It's kind of like, just sanding something is what we're doing. And so we start with the lowest grit that we have, and we put all of our samples face down on it. And then what's super cool is that some little arms that are going to come out of this little head right here, and it's going to hold our sample down to the sandpaper as both of these, as the sandpaper spins and as our sample head spins as well. And so it is really nice because I can just press a button and then it does all of it. Whereas, before we had this, we had to sit here and we had to, you know, do it by
Oh,
hand. And it was really hard and it was hard to be consistent. Um, so this makes it much easier. So yeah, I'm just putting a little sample head down and putting my samples in. I have quite a couple here that we can work with today. And then another cool thing is I don't know if you can see it, you can kind of see it back here, but this is going to dispense water because if there's no water, we need some type of lubricant, uh, or it will grind away our sample too fast. So we always use water when we're grinding, and then we use something called dilute blue for whenever we're polishing. And these are like the final steps. But yeah, that's just what I'm doing right now.
that's super cool. So I'm guessing you're needing to polish it in order to make a very smooth surface, like for microscopy. And I
Yes.
imagine if you're doing that by hand, does it very much matter if it's not like a completely level surface in terms of being able to see with the microscope, like
Yes.
high resolution of the whole surface?
Yes, it matters a ton whether it is flat or not, which is the hard part of doing it by hand. And I actually have one here that is very not flat. So you can kind of see how one side is darker and one side is lighter.
Right.
So that means that only the lighter side has been getting polished, which means it's not a flat sample. And even if I hold it up, you can kind of see that it's
Uh,
not flat at all. And that's because this one was first done by hand. Because actually here at LSU we have a materials lab for the mechanical engineers, uh, which I was a TA for, and I also graduated from LSU as a mechanical engineer, so I went through that too. But whenever they do this lab, they have to sit there and do it by hand. So this is actually one of the samples that they did, and we call it beveled. So it's super beveled. And yeah, if we don't have a flat specimen for a microscopy, it's really hard to focus the sample. You'll get like one side of the sample that's out of focus, one side of the
right.
sample that's not in focus. And then if we're doing even more advanced stuff, like energy dispersive spectroscopy, which tells us a lot about the chemical composition, that is super important to have a flat sample for because the x-rays that come off of the sample, which is what tells us what it's made of, that can really be affected by any kind of topology that's on the sample. So any kind of roughness or uneven surfaces. So that's why it's really important to have a flat sample and why the auto polisher is perfect because it takes out that human error. But yeah. So I get to
That's
just press a
awesome.
button and then it goes and I don't have to do anything. Yeah.
Nice. So can you tell us, like, to back up a little bit, like what kind of samples do you study in your lab, in the Epic lab at LSU? And yeah, I mean, I mentioned geology because I think about rocks or, well, I guess even metals. I don't know. I think about all of these things are things you can source from the earth, but
Right.
to some extent, but you're combining them in unique ways. Yeah, like
Right.
where does material science fit into like science in general related to geology and like natural products you would find
Right.
on Earth?
Material science is super important for just figuring out, what materials work best for what specific use cases. So the largest one right now is essentially what material would you want to make a rocket ship out of? You know, so it's figuring out like, well, the rocket ship is going to be under very extreme conditions and it's going to reach really high temperatures and all this kind of stuff. So, what people were doing way back then, they figured out a certain material to make rocket ships out of. And now a lot of the technique is being used to study kind of more novel stuff, like something cheaper or something more efficient, something lighter, which would be make it more efficient. And so all of that has to start at the research lab first, where we do all of these small scale testings and all of this kind of stuff. So, for example, if you want something for like extreme temperatures, we're looking at a copper alloy right now, and we want it to be stable at super extreme and high temperature. Well, we're looking at what if you add tantalum to it? Is it going to make it more stable at this high temperature? And then we can see that, oh, well, it does make it more stable, but it also introduces this other defect that we don't want. And so we're like, okay, well, what if we add lithium to it? Then maybe the lithium will, you know, negate that defect that we don't want, and it'll also keep the copper stable still. So that's kind of what we're looking at. And what we call it process structure property relationship. So how does the process, i.e. ball milling or thermal spraying or something like that, how does it affect the microstructure of the material? So we're looking at the inside of the material. And how does that affect the properties? So hardness or stability at higher temperatures and stuff like that. So yeah, it's basically the very first step to creating, or the very first step to, you know, introducing a new material for a specific use case and identifying if there's anywhere in the industry right now that needs that there's a problem with a current material, and if they need a new better material, how would we make that? And we look at it on a very fundamental and very experimental level.
That's super cool.
Yes.
Yeah, that's amazing. Yeah, I think one of the first projects I learned that your group was doing was copper alloys, which like I didn't, you know, I am a scientist by background, but definitely not a material science. So the point of an alloy, right, is like mixing some other metal with the copper and you can have unique properties, right? Isn't it true that copper, you have this like conductance, like you can use it for electric carrying electricity in a wire, but it's not necessarily very like strong. Maybe it's very
Yes.
plastic in a way, like
Yes.
it's not good for, I don't know, wartime uses where you need something very strong but still needs to conduct energy, or for going to, being on a rocket ship, something that can't break.
Yes.
So by like adding these other materials in, you want it to maybe still be conductive or still conduct electricity, but also be very strong. And also, and it's incredible like how much science goes into like making that true and like playing with those different
Mm,
compositions of different types of metals, different how much of it do you add, and then even like the structure that you can't see
yes.
on the like smaller than the human eye can see, how the atoms are layered together also matters, which is just kind of crazy to me.
Yeah, I mean, it's crazy to me too. Like I just finished my first year, so there was a lot that I didn't know and a lot that was just crazy to see for the first time. Like you mentioned, like at the atomic level, like a lot of the electron microscopy, as you know, that we do is at the atomic level. So we have a super fun, extensive microscope here at LSU that's very popular, and it can go down to the atomic level and we can see atoms with it. And just seeing that for the first time was really crazy because you kind of look at atoms, in your sample and you're like, nobody has seen this before. but I have seen
Yeah.
this now. So it's really fun and it's exciting. And truly, you're right. Like, you'd never realize how much work goes into creating the materials that we use for everyday life and how important what's going on at an atomic level and inside the microstructure is for those specific uses. It's mind blowing to me how important it is. You can't just like make a material and expect it to work for whatever you need, you know?
Right. Can you maybe, do you have an example of that? And I mean,
Yes.
I guess when I think of it very superficially, it's like the idea of like, let's say you mix these two metals together, but if you don't mix them well, you might have a big pocket over here of
Yes.
copper and a big pocket of your other metal, like, I don't know, a smoothie that's not well blended, right? And then that would make it so maybe it would break more easily on that in that pocket, or maybe, it's not, the properties aren't the same throughout, which I mean, in our day-to-day life might not be so important. I don't know, for something that like, I don't know, an umbrella, I don't know,
Right.
something, but like when it is a talk, we're talking about a rocket ship or something that's under extreme circumstances, it becomes very important, right?
It's kind of interesting that you say, like ideally we would want something, or this pocket might make it break or do something undesirable, if you will. But really, what's super interesting is these pockets actually, we could call them precipitates, which is what we call them, and specifically in the copper tantalum lithium alloys that we were talking about, we actually add the tantalum into the copper as well as the lithium, and then we heat treat it. So we heat it up in a furnace in order to create these kind of pockets. So you'll
Oh,
have like a phase, is what we call it, that is separate from the copper matrix. And these separate phases, which we call precipitates, actually make the material more strong, and more stable. So sometimes we do
interesting.
want those, different phases present in our material because they do help out the properties of what we're wanting to achieve. So, and that's the other part is you're just like baffled, like, you know, wait, you're saying that this little tiny precipitate, it's probably like 2 nanometers in size, it makes the material much stronger and much more stable at high temperatures. So sometimes we do want that. But at first we do want it to be homogeneous. So that's why we ball mill it. So you have to ball mill it to get a homogeneous mixture, and then you anneal it in order to get these precipitates to form, essentially.
Interesting. Okay, yeah, I do remember that now.
Yeah,
I
I know.
remember you explaining that there this copper, you put some different metals in the that formed these little pockets, and then
Yes.
explain why does that make it stronger? It was like kind of
Right.
so that like a brake line can't go straight through the material, like it kind of bounces around the pockets, or
Right. So a material deforms, is what we call it. So it will deform whenever there is dislocation motion in it. And you can think of like a dislocation like a worm, kind of. It's like we call it a line defect. And so it's basically where there's mismatch in the atoms, and it creates a lot of strain in the material, and it wants to move ideally just to reach equilibrium. So you can think of it as like a worm moving through dirt, essentially. And as that worm is moving, it deforms the material. So it makes it weaker. Our material is bending, and we don't want that. We want the worm to stop moving. And so what you can think of is if the worm is like moving around in dirt and it hits a rock, like it can't move through the rock. So that rock is going to be our precipitate. So we essentially have these precipitates to stop that dislocation motion. And that's what makes our material stronger and less likely to deform. But
that's, yeah, it's
yeah.
so cool. I mean, do you have ideas of what's gonna happen when you're putting these materials together? I mean, you have, I guess, hypotheses about, if we add these kind of things, maybe we'll get this atomic structure and then it'll make it stronger or whatever, lighter.
Yes.
Or do you just kind of mix things together and see what happens?
Well, for me, I'm kind of in a special case right now because I got my bachelor's degree in mechanical engineering. I don't have it in material science. And we take maybe 2 classes on material science. So I'm not super informed on it. I've only been working in this lab for, I think, 2.5 years now. And so what I've been doing is I have been just putting stuff together and seeing what happens. But as I take these grad classes, there's two big things that we need to look at essentially, and that's going to be the thermodynamics of the system and also the kinetics of the system. So you kind of look at things called phase diagrams, which tell you at what compositions and what temperatures a material system will exist at. So one of the materials that I'm working on right now is aluminum magnesium. So I have to look at a diagram, a phase diagram of aluminum magnesium, and I can look on this diagram at what percentage magnesium, at what temperature, is it going to be a liquid? Is it going to be a two-phase? Is it going to be just purely aluminum phase? You have to look at these diagrams and you have to figure out what concentrations work for your use cases, essentially. And then you have to look at the thermodynamics, I mean, and then also the kinetics, and that tells you essentially like where the atoms go and how fast they go, essentially. So there's actually so much going on whenever you pick these material systems that you have to think about. But at first I was not doing that, and I was just mixing stuff together and hoping that what came out was good. And it very rarely was actually good. So I would have to sit
Oh,
down and look at these, all of this theory about what is going to happen whenever we mix these two materials together and what we what we get out of it. And then you have this theory of what you think is going to come out of it, and then you put it in the microscope, and you're like, "What the heck? Like this is not what we expected." And then you can write a whole paper about it because you're like, "Hey, we thought that this thing was supposed to happen and it didn't, but look at this other cool stuff that we found." So
yeah.
that's kind of the
I think that's
process.
the cool part of science, though, in a way, that, of course, when we're going to create something for a very particular use case, we want to be efficient about it, I suppose. And,
Right.
you know, let's say, the Army gives us a project. We want to say, okay, let's be informed, pick the right materials to test. But in a
Yes.
way, some of these other random things that come out of it that end up being innovative or that people hadn't thought of before. I
Mhm.
do think, I mean, sometimes that comes out of people who may be coming from a different field
Right.
and don't necessarily know what they're doing, but they kind of don't observe the rules, and sometimes good things come out of that too.
Right.
So
Exactly. No, you're completely correct.
so how long does it take to polish like one sample?
It usually does not take too long. We go through 3 different levels of grit, which is what I've been grabbing over here. And I'll do typically a minute or 2 minutes. I've been letting them go a little bit longer just because I've been talking. Um, and so that's going to be for grinding. And then we have special polishing pads that are located under the machine. And those I'll do for 2 minutes per side or per polishing. And then that's about it. So whenever we were doing it manually, it was much more annoying and timely. But now it probably takes me about 20 minutes to do one sample.
Nice.
And the other good thing
Nice.
is that this holder holds 4 samples. So I can do 4 at a time instead of having to just do one like we used to. Oh,
Nice. Yeah, I'm sure your hands got tired after a while of doing it manually.
yes. And then you have to like press down so your shoulder gets sore and it's just not fun.
So yeah, did you grow up being interested in, like, how did you get into this field? And is this where you thought you would be when you were, I don't know, younger?
This is definitely not where I thought I was going to be, which I think which I think is most common with a lot of people. You feel like you never really expect to be wherever you end up. Um, I was always super interested in space when I was younger. I really loved NASA. I loved all of the NASA initiatives. My favorite NASA initiative is the space shuttle program. And so, yeah, I was always super interested in NASA. And so I was like, I'm going to go be an engineer because, NASA is always looking for engineers and I really want to work on a rocket ship, say. And so I went to school for mechanical engineering, and I thought that I was just going to get my bachelor's, get a job, and that would be it. And I would be like this super cool aerospace engineer. Um,
Nice.
but then so I was going to have an aerospace minor so that I can be more attractive to people who wanted to hire an aerospace engineer. And I took one aerospace engineering class and I was like, I'm out.
Oh, really?
Yeah, I was because it was called gas dynamics and it was a lot like fluids. And I was like, I just don't want to be a part of this. I was like, I'll figure out something else. I wasn't too concerned at the time because before gas dynamics, I had actually taken a class called composite materials, which is about composite materials, which is completely different than what we do in this lab. So composite materials is going to be something like carbon fiber suspended in like epoxy. And it's a very new hot material right now, or class of materials, if you will, for like wind blades, wind turbines, and stuff like that. And so I really liked that class. And I was like, wow, materials are really cool because you never think about what goes in to, why your pan is made of cast iron, or like
Right.
why the nonstick coating on your pan works. You never think about that. And so much thought actually has gone into it, from other scientists. So that was kind of like my introduction to how important material science is. And actually, I was taking the composites class and I was like, wait, this is kind of like, instead of saying like designing the shape of rockets, this is like designing what rockets are made out of or figuring out what rockets are made out of. So I was like, this is an interesting pathway into aerospace engineering, which I didn't think was existed at all. Like when I thought of aerospace engineering, I thought of designing a rocket, designing
Gotcha.
what,
Like the shape of it
yeah,
and like
exactly.
right.
And, or a satellite, or how to efficiently move through a fluid, you know.
Gotcha.
And so that's what I always thought aerospace engineering was. But I figured out during the composites class that actually materials is also super important. What the rocket is made out of is super important. So that's why whenever I took gas dynamics and I didn't really like it, I was not too concerned because I was like, there's actually this whole other field of aerospace science that I can go into and still work on what I'm passionate about. And so I I didn't like gas dynamics, so I dropped the aerospace minor. But I
Was it
actually,
just very abstract or a lot of math or like
yeah,
what
it was
was
like a lot of math because it was essentially like you would work on essentially like fuel coming out of a rocket, like the most efficient velocity that fuel should come out of a rocket and stuff like that. Like it was just very and it was just like very not what I was about, really. Um
right?
and not what I was good at because at LSU, fluids is one of our hardest classes as a mechanical engineer. So it kind of just
Gotcha.
felt like fluids again. And I was like, that class is so hard.
You're
I
like,
don't want
I
to
already
relive it. Yeah.
gotcha.
But what really got me into this lab specifically was when I took a tech elective about electron microscopy. That's when I really started to get passionate about materials because electron microscopy, I didn't even know that it existed. And seeing what these microscopes can do was just crazy to me. And I really liked operating the microscopes. I really liked seeing, like putting stuff in them, seeing them. I put a bug in one time. Like it was just really fascinating to me. It was just kind of like I kind of went through like my mechanical engineering degree kind of not lost, but like I didn't know what my niche was. I always said I wanted to do aerospace engineering, but I didn't really have a niche until electron microscopy, which is a big part of what I do in this lab. So my boss at the time was teaching the class, and that's kind of how I got involved into this because I really liked it. We spoke, and then we decided that I should work for the lab and come learn some more advanced electron microscopy techniques. And so just learning all of those techniques and what we can see and the material was just super fascinating to me. And
Yeah.
then, you know, full circle moment, we now have this NASA grant that we work with Lunar Regolith. And so it's like, no, well, I guess you can kind of say like, yeah, I always expected myself and wanted myself to work with NASA or on something space technology related. And I kind of got lost there in a second, but then I kind of came back now with this NASA grant. So now we're working on that special project with the regolith in a way that I never would have expected. So that's kind of how I got into it. I would say my gateway into material science was the electron microscopy. That was super fascinating to me, and how I got into it. And now I'm, doing powder processing and powder metallurgy.
That's super cool. It's kind of mirrors how I was also an engineer, but similarly, like like straight math or fluids, some of those classes were definitely not my forte. Like I got through them, but
Right.
I was a biological engineer, so I focused on the biology more and just also fell in love with that confocal microscopy, like
Yes.
basically being able to see things that the human eye can't see
Right.
and being able to take really get beautiful pictures with confocal
Right.
where you can see, a whole new world, right?
Right. Yeah.
And discover that. And I feel like, seeing is believing very much for me. And so it was just so cool to, have that. And I think related to what you said, is very powerful in terms of like, I feel like when we have a goal, it's like, I want to work, you know, in the space field. It might not turn out exactly the way you want it to. Like, I was recently talking to Renee Horton. She is an LSU grad, studied engineering, and she really, really wanted to be an astronaut. But she had found out that she had, when she went to apply, that she was hard of hearing. So it was like, definitely not, can't be, never, could never become an astronaut. And she really felt like her dreams were completely dashed
Right.
until she started working for NASA Mishu. She actually ultimately helped do a lot of the like um, welding, and I'm not going to say it properly, but very special types of welding for building the basically the boosters that got us to the moon recently,
Right. Right.
or orbiting the moon. So very much she's like, I never became an astronaut, but I helped build the thing that now is sending many astronauts to the moon. She's like, that's a pretty awesome goal too. So I
Right.
think kind of being open to like, I think anything you set your mind to, you really can do, but it's not, doesn't mean it's going to be exactly what you thought it was going to be.
Right. And that's the other thing too, is I never imagined myself in grad school as well. That was never once on my radar, never on my plan. I thought that I would get my mechanical engineering degree and then go be a force to reckon with in industry. But, one thing led to another, and here I am dedicating another 4 years of my life to LSU. So, but it's just it all just came from, what really just gets your mind going and makes you really happy to show up. And that was the research for me. So yeah.
That's super cool. Well, you mentioned the lunar regolith, so um, can you tell us a little bit about that project? And it's just, very cool in terms of it being very timely with the moon missions.
Right,
And I
right.
just think it's, yeah, fascinating. It may be related to that box back there in terms of like needing to make flammable
Yeah.
materials in the absence of oxygen.
Yes, exactly. So it goes along again. So our uh, Lunar Regolith project goes along with our experiments of just adding materials with other materials and seeing what happens, really. Obviously, we don't just see what happens, we have a plan first.
Right.
But basically, it's really interesting. So obviously, with all of the Artemis missions and stuff like that going on right now, there's a big initiative called In Situ Resource Utilization by NASA, which means we want to use all of the resources we can that's present on the moon in order to do things like build small scale structures, repair structures, and stuff like that. So essentially, we are trying to figure out a way to use the moon dust, which is obviously incredibly abundant on the surface of the moon, in order to produce usable materials for manufacturing, repairing, and stuff like that. So our idea was we're going to take lunar regolith, which is essentially moon dust, and we're going to combine it with lithium hydride. So moon dust is composed of a ton of oxides. So it's got iron oxide in it, it's got aluminum oxide, magnesium oxide. And what we want is we want to separate that oxygen from the metallic component. So we want to take the oxygen away from the aluminum, which is what we're most interested in the regolith. And we want to just produce pure aluminum so we can use it for structures on the moon. But first, we need to make it not be bonded to oxygen. So that's where the lithium hydride comes in. So earlier I was talking whenever we, mix two materials together, we have to look at a bunch of diagrams, we have to look at a bunch of the the kinetics, and see if what we want to happen will actually happen whenever we add them together. So lithium likes oxygen way more than aluminum does. And we know this because of the thermodynamics. So we are ideally hoping that by adding the lithium into it, whenever we ball mill the material or mechanical alloy it, so we're adding mechanical energy into the system, which is going to be inducing a reaction. So that is essentially the reaction is the oxygen moving from the aluminum to the lithium. And we know that the oxygen wants to move from the aluminum to the lithium because of the thermodynamics. We just need to give the oxygen the energy to move. So that's where the ball milling comes in. So we ball mill it so that we can give the oxygen the energy to move from the aluminum to lithium. And then after that reaction occurs, we'll have lithium oxide and aluminum. So it's called a redox reaction, where you basically reduce an oxide, and then you're left with the metallic form of whatever was in the oxide. So we'll have just the pure aluminum. So that's kind of what we're doing with the lunar regolith. And you're right, the Vox is super important for this project because obviously there's no oxygen on the moon. And so we're trying to simulate the conditions of the moon as closely as we can as possible. So we ball mill the regolith and the lithium inside of an argon environment, which simulates the moon's atmosphere. And then also, it is much safer to deal with lithium when it's not in an oxygen environment. On the moon, there's no oxygen, so we can handle it whichever way we want to. And it kind of gives us a way to use up the lithium that's on Earth too. So there's a couple different good caveats for using lithium as the reducer, other than, say, magnesium, which magnesium also likes oxygen more than aluminum does. But we chose lithium hydride instead. Or we chose lithium, but we have to have it in the form of lithium hydride in order to safely handle it on Earth.
Gotcha.
But yeah, that's the moon project. That's our NASA project right now.
Yeah. Well, you mentioned lithium in terms of it's not safe, but I mean, lithium is also something we use in batteries, right?
Yeah.
Like, and why batteries are, we talk about like fire risk with batteries.
Right.
So is it like, yeah.
So lithium is super pyrophoric. So if you expose it to oxygen, it just likes to combust and light on fire. And I've had a couple incidences, unfortunately, where I've had my sample not completely light on fire, but there was some red going on. But yeah, I've had a couple. So that's what lithium likes, to do when it's exposed to oxygen. And that's a big reason why you're not allowed to have like your laptop chargers in your checked bag and on airplanes, because if it starts a fire, which it's very risky that a lithium battery would start a fire. It's obviously very unsafe. If it's under the plane, then in your carry-on where they can easily extinguish the fire. So yeah, that's the other caveat that we've learned with working with lithium is how to minimize the risk and also make sure that we can properly observe it in a moon environment.
So yeah, I mean, I was wondering, as you were describing this, a question came to my mind of like, I mean, I just started to see, okay, you're getting the oxygen off of the aluminum, how do you then like get that aluminum, the pure aluminum, like out of that sample? I mean, I'm imagining like a sifting thing to like where you would sift for gold. Like
Right.
how how is it still mixed in that material or
So one common way that we've seen something similar done is that you can just melt the entire system. So if we react the lithium with the aluminum oxide and we get our aluminum and our lithium, well, if we heat it up, they all have different melting temperatures. So we can kind of put
um
it in a big pot with a hole at the bottom and then heat the whole thing up. And then each material, pure iron, pure aluminum, pure magnesium, will all come out at a different time because it has different melting temperatures.
uh,
And so that's kind of one idea that we have of separating it. Right now, we're at the very early stages of the project. So just seeing how ball milling affects lunar regolith, how lithium and regolith mix together. Like, what does the microstructure look like? Is it homogeneous? Is it layered? That type of thing. So we're trying to just figure out how all of these different processes are actually affecting the powder. And then way in the very future, we're going to be starting to figure out how effectively we're reducing the oxides and what's a good way to separate the oxides essentially. But yeah, that's
that's
just one
super
idea
cool.
that we had.
That's super neat. I think it materials are so cool. Like you mentioned the on the electron with using the electron microscopes, I didn't really think about that either, that like being able to characterize these things, you know, at that atomic level, you're able to yeah, create and test materials that would be like ultra performative or you know exactly what you expect them to be, especially when you're talking about sending them on a mission to the moon, you wanna make sure that the
Exactly.
you know exactly what's gonna happen with that material.
Yes, exactly. So if we're going to spend the money and the time to send stuff to space, we need to make sure that it's going to actually do what we expect it to do.
Yeah.
And that's where a big motivation of our research comes from.
What's a current struggle for you, I guess, in science more generally, or you're in your career or in science communication? I don't know, something that you're currently working through or
That's a good question. I would say one of the hardest things is being okay not knowing things, at least for my personality type. Um, and my professor was just talking about this yesterday, how he said, whenever you graduate with your bachelor's, you think you know everything. And you're like, I just did 4 years. I know everything. I'm ready to tackle the world. Well, if you do grad school, you get into your first year of grad school and you're like, I know nothing. You realize how little you
Yes.
know.
I know.
And so you're slowly just like building up, climbing this hill of knowledge that you need to learn and, to do your experiments with. So that's like a huge thing that I'm struggling with right now is just reading the papers, redoing my experiments, thinking really critically about everything that I'm doing, which is why I really like research because it makes you think so hard about what you're doing and what is efficient and what's making sense and that kind of stuff. And yeah, you realize like how little you do know. And so that has been a struggle for me for sure. Um, but yeah, I would say that's my biggest one is just kind of being in an unknown state all the time, not knowing
It's
really.
it's so true. It's crazy that the yeah, the more educated you get, the less confident sometimes you are in your abilities, and it just gets worse.
Yeah, it's
And
true.
then and
The
it's had some interesting parallels in science communication. So there's like some science communication studies where people that have just like kind of your just enough knowledge on something are actually like the least, sometimes the most entrenched in their beliefs, like in terms of not changing their mind when you present them with data because they're like, no, I know this, right? But they're almost at that like, I know enough, just enough to be dangerous, which like I'll say a lot, right?
so
But
real, yeah.
it really is. I mean, like knowing a little bit does make you kind of dangerous because you don't know what you don't know, but you have this
Exactly.
feeling that you know things that you don't.
Yes.
Um, so like unfortunately, I'm staying in that curse all the time because I am a generalist. So I know a little bit about something, a little bit, now I'm after this podcast, I'll be like, oh, I know about material science, and I really don't. But but yeah, it's very real that even in my specific area that really I know a lot about, sometimes I'm like, I don't, what do I know? I don't know anything. Like,
Yeah, and then not only like with not knowing like specific, your knowledge gaps and stuff as a researcher, it's also like, when I was an undergrad, like I thought that I was going to just go get an industry job. And like that's kind of what my plan was. And so now as a grad student, obviously I didn't get an industry job and stuff like that. And so now I have to think, well, what do I want to do after grad school? It's like, do I want to go into academia or do I want to get a research job? Do I want to go into a higher position in industry? And you're exposed to everything as a grad student. Like you're exposed to how academia is, you're exposed to how intensive research is. And so it's also, at least again for my personality, it's been a struggle of not knowing what I want to do outside of grad school yet. I have all of these interests and all of these things that I'm really enjoying, but how do I want to put that together into a career? That's the other thing that like I'm not fully aware of yet. And you just have to kind of be comfortable with the uncomfortable, but whatever they say,
right,
not knowing stuff. So that's
right.
the other thing, yeah, that I kind of struggle with. But
Yeah, I can very much relate. I think for a long time after, well, yeah, when I first graduated with my PhD, I also like had this idea of what I was gonna do. Like, I think just going through that experience, you start to become more and more like academia starts to feel like the comfortable thing. So I'm like, okay, that's it. Gonna stay in academia and become a professor. And then for a variety of reasons, it just wasn't working out. Like, I didn't really want to follow the like postdoc. I didn't want to move
right,
everywhere, and wait. So I kind of was like, well, that's not going to work. And then, you know, my alma mater wasn't going to hire me because I got all my degrees from there. Like, it just became this like, what do I do? And I
right.
remember crying for months after my PhD, like kind of in this like, what am I doing with my life? And
Yes.
then, and then you just kind of, my philosophy is just to say yes to things. So
Mhm.
like opportunities came up that I didn't know were going to exist, and I would just kind of say yes, and like things started to like build, and I've had, great opportunities along the way, and it kind of like, shapes you, and it's great, but like I feel like maybe when I was younger, I was like always afraid if I made a very definitive step in one direction, it would mean like all these other options aren't available anymore.
Yes.
And then just starting to realize that that's not true. Like you can step in that direction and say, you know what, that wasn't right, and go step in the other direction. But when you're when you're just starting out, it feels like a very hefty decision to make.
Oh, 1,000% it does. Yeah. And so I try not to think about it and I take every day as it comes, just whatever. I solve the day's problems first and then I kind of think about other things after the day.
I think that's a good philosophy.
Yeah, it's true. It's kind of how I stay sane.
Well, you've been doing a lot of science communication too, during your PhD. The Epic Lab, I feel like, has gotten some good exposure. You've done some videos, you've done some media reports about your various studies. How do you think about science communication? How is that becoming important to you?
Well, my personal philosophy is that over half of the reason why you're successful is because you're a good communicator. Like I think that communication is everything. I think, whether to get jobs, to get funding, to get, you know, anything, like you need to be able to communicate why your work is important. You need to be able to explain your work to people who aren't experts in your field, who know nothing about your field. You need, or to people who want to get into your field, like, mentoring undergrads and stuff like that. Like you have to be a good communicator to achieve a lot of stuff is what I have seen. And it is what I, have and it's what has worked for me. Like as a mechanical engineer undergrad, a huge stepping stone is at your internships. Like you need internships.
Right.
And so that's how you get like a good job as a mechanical engineer. If not, then you will just have to just take what comes to you after you graduate. Whereas if you have all of this experience, you can kind of be a little bit more selective. So whenever I was an undergraduate, that was like obviously I didn't see myself in grad school. So I was trying to get as many internships as I could and as many opportunities as I could so that I can like fill out my resume, just become this good candidate. But I didn't really have good grades. I was not the best student. So I had to lean on my communication skills. And I'm pretty sure that's why I got my internships. I got slightly more than the average mechanical engineering student would have. And I
That's
really
awesome.
think it's because I was able to communicate what I was working on, communicate what I was good at, also be very clear and upfront about my weaknesses. I think taking accountability and understanding where you fall short is also very important. But I just think that it is 90% of the reason of your success is that because of communication. And obviously, not only does it help with your career and everything, but it helps with your relationships with your friends and your
Very true.
partners and all of that kind of stuff. So, like, me talking to you today about my research, like, could help me in a couple months talking to my husband, just because, like, you get that practice in and you understand how to better communicate your feelings and how passionate you are about some things and why you're passionate or why you hate other things. I just think communication is the key to everything. Like I'm super opinionated about it. Um, but yeah, like so we've been getting lots of opportunities to showcase the work in our lab. And so we've been having a lot of opportunities to communicate our research, why it's important, and then that helps us get other opportunities
Right.
because we are able to communicate so clearly, essentially. So, like, if
Yeah.
anybody takes anything from this podcast, it's practice communicating. Because whenever I was in high school, I was like very quiet, and I still can be quiet sometimes. And I was never one to, speak up or whatever. But I actually started serving tables whenever I was in college, and that changed everything. Like I'm a completely
That's a
different
good,
person
yeah.
because you have to communicate. You have to build a relationship with the people, that you're serving and stuff because you want tips. You want money. So that like literally changed everything and changed the outlook that I see on life. And developing relationships is all about communication. And all of that kind of stuff. Like I developed a really good relationship with my boss, my advisor, and I think it's all just because of the way that I was able to portray myself and talk about stuff. So, yeah, I'm very passionate
Yeah.
about the importance of communication.
Yay. Obviously, I'm biased. I very much agree as a science communicator, but um, no, it's funny. You never really, never know what's gonna help you become a good communicator until you do it. Like you said, waiting tables. I was
Exactly.
also very shy, very quiet. I mean, I was homeschooled, so you can imagine. And then I came to LSU. I was a student athlete, so that already kind of opened me up a little bit.
Mhm.
But I really didn't do any communication until I decided I was, in a biomedical engineering degree, and I ultimately decided I wanted to do science communication. So I switched and I started a PhD in mass communication because, that's what you do. If you're me, you just get more schooling to learn how to do the thing you want to do. But my first class that I took was a crisis communications class, and the professor was really encouraging us to like practice crisis communications. And one of our big assignments was to find someone who had been in a crisis related to something we were interested in and to interview them. And so me being, wanting to do science communication, I found someone who was in a chemical lab, like a science lab fire, who had gotten very badly burned. And I wanted to interview them about this and become very much a proponent, right, of like lab safety and also like um, beauty, no matter what you look like, kind of thing.
Right.
And I remember being terrified to speak to this person. Like I was gonna I set up an interview to call her, and we had gone through like all this like how to interview, how to like be very kind of empathetic in interviews, like not further triggering someone's trauma, right? But being like respectful to like letting them go at their own pace, like all these things to like how to interview people that were victims of a crisis without kind of like taking advantage or pushing them further, into trauma. And so, and I was terrified. I was like, I'm gonna like ask the wrong questions, about this incident. Of course, this person was so used to speaking about this, like they just took over. All I had to do was like, hi, I'm a student and this is my assignment. And they just this girl was like so kind and such a good interviewee, and kind of told me her experience. But like going through that class and getting that practice was so I came out of that a different person very much in terms of like, I'm a very much of an introvert, but get me in front of a scientist and, I can
Right.
talk all day.
Right.
So, yeah.
It's 100% true.
While you've been polishing, are you
Yes, I'm
ready
ready.
to
Ready to
put
put
something under
them.
the microscope?
Yes, yes, I am. So I can move
Sweet.
my camera. We have two like optical microscopes right here. So we have one right here, and this one actually is also a um, hardness indenter, a micro indentation system. So we can actually take this and we can punch a hole in our sample or a little indent, not really a hole. And we can do that a bunch of times and we can measure the hardness of our samples.
Yeah.
So I have one in here right now that I'm going to take a bite. Um, and so yeah, this machine is also just important on our processing structure property relationships. So we, process a powder and we characterize the structure of it, and then we test its properties. And so one of the properties that we do is hardness. And so that's a good indicator of how strong the material is. So our light optical microscopes are super, super simple. You just your sample in. The light optical microscopes are really good because we can see how well we polished our samples. Because we don't want a ton of scratches whenever we are looking at our samples under the electron microscope. So that's what the polishing and grinding is for. So they can be super clean and super awesome. So I didn't polish these ones very good. So you see,
we were chatting too much.
yeah, but it's okay.
Sometimes that's how science goes, especially when you're chatting through your science.
Exactly. And it's all a-okay too. It's really not that serious. I don't like to take research seriously. Don't tell my boss.
Sometimes it's important to not take it too seriously because there's a lot of times that things don't work, right? Like
Exactly.
how
Exactly.
often do you polish and it's perfectly polished?
Sometimes I will polish my sample to oblivion. It won't exist anymore, and then I have to redo everything. So like
Oh no.
you can't get too attached to anything in this lab really, because you don't know if the funding is going to get cut or you don't know if your powders are going to light on fire and you're going to have to redo it, or you're going to grind away your sample. I have grinded away way too many regolith samples, unfortunately, because the lunar regolith and the lithium hydride is very tricky to grind and polish. We actually can't use the auto polisher. We have to manually polish it with something that we
Really?
3D printed because the lithium hydride actually reacts really crazy with water. So we have to
Oh.
find another novel way um, to polish it. But yeah, it's super crazy. But don't take research seriously and you'll be happy.
Yeah.
I'm like not kidding.
I mean, I hear you. I can't tell you. And that's probably why I got out of research because there was way too many times that I was doing an experiment in the lab with cells. I mean, especially living, cells and doing
Right.
experiments with them, and the amount of times they would get like contaminated or
Right.
like die for some random reason.
That's the other thing. Like I have it is that research is not for everyone, unfortunately. As much as I would want everybody that I mentor to go into research just like I did, it's not for everyone. Like I mean my best friend and my husband both decided to get their masters, and then after they did their masters, they were like, can't do it anymore. It's not for me. They get too attached and they don't like it when things don't work out. They don't like how slow things take sometimes. It's very not for everybody, and it takes a certain personality type to really enjoy it. One, and then also be good at it. I think a lot of people can be good at it, but I would say it takes a very certain personality to enjoy it, at least. And you want to enjoy what you're doing, obviously. So that's
Right.
the most important
How
one.
do you keep that? How do you keep that distance? Like, how do you not get too attached? I know, like, if I spend a lot of time at something and it doesn't work out, I get really, yeah, I'm bad because I'll get really upset. Like, I spent all that time on it and like it didn't work.
I don't really know how I do it because sometimes something will take a long time. Like say you want to do like a super long anneal. You want to put something in a furnace for a super long amount of time. And you expect to have a certain kind of result. And then you put it in the microscope and you don't see that result. And you're like, this took me so long to do. And I'm going to have to do it again. And it's going to take a really long time. And it is very frustrating. But what I like to do is I always think that there's like a reason for everything. Like there's a reason I messed up this experiment. What can I learn from this experiment that I messed up? Really. And by framing it that way is how I really stay being able to engage with my work in an enjoyable way. Is just always learning from my mistakes and not getting too hung up on them because I realized that, well, it's important that I failed this way too. Because in engineering, a big quote that everybody says is fail hard and fail fast. So
Right.
sometimes we can't fail fast, but we do fail hard. And you just have to take everything that you can and learn everything that you can from that in order to more efficiently move forward. So instead of framing it like I failed, I did the experiment wrong or something like that, you can just say, what did I learn from it? And how is that going to help me? And I'm always like, well, I failed so hard at this thing for a reason, and it was so I can learn this one specific skill or knowledge gap that I have. So it's all about reframing your mind. But of course, sometimes it is hard to think like that. Sometimes I do get frustrated and I have to take the night off and try not to think about work. Um, but the
That's
fun
really powerful though.
yeah,
Yeah.
yeah. And the fascinating thing is like when you fail hard like that and you're really frustrated and you're like, I need to take the night off and not think about work. Well, you're not thinking about work as you're making dinner and whatever, and then you fall asleep and you're like thinking before you fall asleep and you're like, wait a second. And then like you kind of get a light bulb moment, like because of this kind of rest period and this big fail that you had. So that is very and that's very fulfilling for me, and so that's why I enjoy this so much, really. But yeah,
That's
but
amazing.
not everybody
That's
can
Yeah, I
do
don't know that
that.
that's I don't know that that's me, but that's really amazing. That's very like I admire that so much, that ability to reframe and say like because it is true. I mean,
Mhm.
you don't learn when you're doing if you get everything perfect the first
Exactly,
time, you really don't
exactly,
learn. You're just like, "Oh, well, it could have just been luck that it worked out perfectly," but you're like, "Well, I did it perfect." So,
exactly.
yeah.
No, I 100% correct. Yeah.
Awesome. Well, Emma, thank you so much. It's been a pleasure chatting with you in the lab. We we definitely have kept you for a long time now, so
No, no
so we'll
worries.
definitely wrap up. But thank you so much. It's been super interesting learning about material science with you.
And I really appreciate this opportunity. I love every conversation that we have. So, I love communication.
Yay.